Preparing for an Elastic software engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How does Elasticsearch use an inverted index, and why is it effective for search? An inverted index maps each term to the documents containing it, rather than storing only documents sequentially. During indexing, Elasticsearch analyzes text, creates terms, and records postings, often including positions and frequencies. A query then looks up relevant postings and combines them using scoring algorithms such as BM25. This design makes text search fast, although it increases storage and indexing work. I would also mention that analyzers determine whether matching is exact, stemmed, case-insensitive, or language-aware. While answering, explain terms, postings lists, tokenization, analysis, relevance scoring, and the trade-off between indexing cost and fast full-text retrieval. Question 2. What is the difference between a shard, a replica, and a segment in Elasticsearch? A primary shard is a partition of an index, while a replica is a copy that improves availability and read capacity. Each shard is implemented using Lucene segments, which are immutable structures created as indexed data becomes searchable. New segments are periodically merged to control file counts and reclaim deleted document space. Shards distribute data across nodes, replicas provide redundancy. I would distinguish shard allocation from segment management because they solve different operational problems. Make sure to cover primary shards, replica shards, Lucene segments, distribution, fault tolerance, scaling, refreshes, and why segment merging affects performance. Question 3. How would you design a highly available Elasticsearch cluster for production? I would begin with multiple nodes spread across availability zones, using dedicated master-eligible nodes and separate data or coordinating roles when scale justifies them. Every important index would have replicas allocated across zones, not collocated with its primary. I would configure sensible shard counts, resource limits, snapshots, and alerting for heap, disk, latency, and unassigned shards. I would test zone failures and recovery, because high availability is proven through failure scenarios rather than topology diagrams. In your answer, talk about node roles, multiple availability zones, replica allocation, quorum behavior, resource isolation, snapshots, monitoring, and avoiding single points of failure. Question 4. What happens when a document is updated in Elasticsearch? Elasticsearch generally does not modify a document in place. An update reads or receives the new source, writes a replacement document, and marks the old version as deleted. The change is recorded in the translog for durability, then becomes searchable after a refresh. Later segment merges remove obsolete data physically. I would also discuss optimistic concurrency controls, such as sequence numbers, to prevent stale clients from overriding newer changes. Be sure to mention near real-time indexing, immutable segments, logical deletion, versioning, refreshes, translogs, and how updates differ from in-place database modifications. Question 5. How would you investigate a slow Elasticsearch query? I would first measure the query consistently and separate latency from the query phase, fetch phase, and network overhead. Then I would use the Profile API, inspect mappings, review shard sizes, and check whether the query forces scripts, broad wildcards, expensive aggregations, or unnecessary source retrieval. I would correlate results with CPU, heap, garbage collection, disk I/O, and thread pools. Finally, I would test a targeted change and compare percentile latency, not just the average. Focus on reproducing the issue, inspecting query and fetch phases, using profiling, checking mappings, shard counts, cache behavior, data volume, and cluster resource pressure. Question 6. What is the difference between text and keyword fields, and when would you use each? I use text fields for analyzed full text search and keyword fields for exact matching, filtering, sorting, and aggregations. For example, a product name may use text for relevance searches and a keyword subfield for exact grouping. If I map everything as text, aggregations become inefficient or unavailable. If I use only keyword, natural language matching suffers. I would define mappings deliberately because changing a field's fundamental type usually requires reindexing the data. Explain analyzed versus exact values, full text queries, filtering, sorting, aggregations, multi-fields, and the consequences of choosing an incorrect mapping. Question 7. How would you prevent mapping explosions in a multi-tenant Elasticsearch application? Mapping explosions occur when uncontrolled fields create thousands of mappings, consuming cluster state and memory. I would avoid blindly enabling dynamic mappings for arbitrary tenant input, define explicit schemas, and route flexible attributes into carefully controlled structures such as flattened fields. I would enforce field limits, validate payloads at ingestion, and monitor mapping growth. Templates can standardize new indices, but I would still review tenant-specific requirements and reject unsafe shapes before indexing. Mention dynamic mappings, uncontrolled user fields, field limits, templates, schema validation, tenant isolation, observability, and safe handling of unexpected input. Question 8. Explain Elasticsearch refresh, flush, and translog behavior. A refresh makes recently indexed operations visible to search by opening newly created segments. It is not the same as a durable commit. The translog records operations so acknowledged writes can be recovered, while flushes create a committed Lucene point and can reduce translog growth. Frequent refreshes reduce search latency but increase indexing overhead. I would tune refresh intervals according to workload, then use explicit refresh or refresh wait behavior only when application consistency requires it. In your answer, distinguish search visibility, durable commit points, transaction logs, refresh intervals, throughput implications, and recovery after node failure. Question 9. How would you design an autocomplete feature using Elasticsearch? I would first clarify whether the product needs prefix suggestions, full text results, or both. For fast suggestions, I might use the completion suggester. For richer matching, search as you type fields or carefully designed edge ngram analyzers may be better. I would test typo tolerance and ranking using realistic queries, while limiting result counts and payload size. The design should keep keystroke latency predictable, avoid expensive wildcard searches, and separate suggestion quality from the main result ranking logic. Cover user experience, prefix matching, analyzers, completion suggesters, search as you type fields, typo tolerance, latency, ranking, and index size trade-offs. Question 10. How would you build a reliable ingestion pipeline into Elasticsearch? I would use the bulk API with bounded batches, adaptive concurrency, and backpressure so producers cannot overwhelm the cluster. Each item needs independent response handling because a bulk request can partially fail. Retries should target transient errors with exponential backoff, while permanent failures go to a dead letter stream. Stable document IDs make retries idempotent, and metrics should cover throughput, rejection rates, lag, failures, and indexing latency. I would also preserve ordering where business semantics require it. Discuss batching, backpressure, retries, ID impotency, dead letter handling, refresh policy, bulk responses, ordering, observability, and protection against overload. Question 11. What is the cap trade-off in a distributed search system like Elasticsearch? CAP says that during a network partition, a distributed system must trade strict consistency against availability. Elasticsearch favors remaining operational in many situations while using primary terms, replicas, and cluster coordination to prevent conflicting primary histories. That does not mean it ignores consistency. Writes may be rejected when quorum or allocation conditions are unsafe. I would distinguish acknowledged durability from immediate search visibility, because refresh timing creates near real-time behavior even when the write is safely recorded. Be sure to mention partitions, availability, consistency, quorum decisions, replicas, acknowledged writes, and the difference between transactional consistency and search visibility. Question 12. How would you design a distributed rate limiter for an Elastic Cloud service? I would define the limit first, per user, API key, tenant, or endpoint, and whether bursts are allowed. A token bucket is often practical because it supports controlled bursts and a predictable refill rate. For distributed enforcement, I would use an atomic state store or collocated partitioning, avoiding read-modify-write races. I would decide whether fail-open or fail-closed behavior is safer for each endpoint, then monitor rejected requests, hotkeys, clock skew, and storage latency. Focus on limit semantics, token bucket or sliding window algorithms, atomicity, distributed state, clock behavior, failure modes, fairness, and operational observability. Question 13. Describe how you would design a log ingestion and search platform. I would separate collection, buffering, transformation, indexing, and querying so temporary downstream failures do not immediately lose logs. Events should carry timestamps, source metadata, a version schema, and a stable identity where possible. I would use data streams or rollover indices with lifecycle policies for hot, warm, and deleted phases, balancing search speed against retention cost. Backpressure, dead letter handling, access controls, and clear ingestion lag dashboards are essential because operational logs are most valuable during incidents. Cover collection, parsing, buffering, schema evolution, index lifecycle management, retention, tenant isolation, query performance, backpressure, and reliability objectives. Question 14. What is your approach to concurrency and race conditions in Go or Java services? I first identify which state is shared and whether concurrency is actually necessary. My preference is to establish ownership, pass messages, or use immutable data before adding locks. When synchronization is required, I choose the narrowest suitable primitive, document invariants, and avoid holding locks across network calls. I use race detectors, stress tests, and deterministic tests where possible. I also consider cancellation, bounded worker pools, and shutdown behavior, since leaked Go routines or threads can become production failures. Mention shared state identification, ownership, synchronization primitives, immutability, atomics, message passing, race detection, testing, and avoiding premature concurrency. Question 15. How would you debug a memory leak or garbage collection problem in a production service? I would begin by confirming whether memory is leaking, fragmenting, or simply responding to a larger workload. I would compare heap usage after collections, inspect allocation and retention profiles, and correlate changes with deployments and traffic patterns. Common causes include unbounded caches, retained request objects, queues, listeners, or oversized buffers. I would mitigate safely with limits or rollback, then reproduce under load and verify postfix heap plateaus, latency, garbage collection behavior, and container limits. In your answer, discuss symptoms, heap profiling, allocation rates, object retention, workload correlation, GC pauses, safe mitigation, and verification after deployment. Question 16. How would you make an API backward compatible while evolving its search behavior? I would treat the API contract as more than its endpoint path. Request fields, defaults, response shapes, errors, ordering, and search semantics all matter. I prefer additive changes, explicit feature flags, and versioned behavior when semantics must change. Compatibility tests should run against representative clients and saved queries. I would deprecate gradually with documentation and telemetry, then remove old behavior only after usage falls below an agreed threshold. Search relevance changes also deserve controlled evaluation, not silent rollout. Be sure to mention contracts, versioning, additive changes, validation, deprecation, compatibility tests, response stability, and communicating behavior changes to clients. Question 17. Tell me about a time you disagreed with a technical design decision. In one project, I disagreed with introducing a distributed cache before measuring the database bottleneck. I explained the operational costs, proposed instrumentation, and suggested a small load test comparing indexed queries, caching, and connection tuning. The data showed that query design solved most of the latency problem, while a limited cache helped one endpoint. I supported the final hybrid approach and documented invalidation risks. The experience reinforced that strong disagreement should improve decisions, not become a contest. Focus on context, evidence, respectful communication, alternatives, decision ownership, compromise, measurable outcome, and what you learned rather than presenting conflict as personal. Question 18. How do you review code for a distributed systems project? I review distributed code by first understanding its invariance and failure model. I look for retry safety, timeouts, cancellation, duplicate delivery, partial failure, ordering assumptions, resource bounds, and race conditions. I also check whether metrics, logs, and trace context make incidents diagnosable without exposing sensitive data. Tests should cover normal behavior in adversarial cases such as node loss or delayed responses. I separate blocking correctness issues from style preferences, keeping reviews rigorous and collaborative. Talk about correctness, failure handling, concurrency, resource bounds, observability, security, compatibility, test quality, operational impact, and prioritizing material risks. Question 19. How would you test a change to Elasticsearch query relevance? I would create a representative query set with relevance judgments from users, domain experts, or historical behavior, while guarding against biased labels. I would compare the candidate ranking with a baseline using metrics such as precision at K, recall, and NDCG, then inspect important query classes manually. I would also measure latency, resource use, and zero result rates. If offline results are promising, I would run a controlled online experiment with guardrails and monitor conversion, complaints, and regressions. Mention labeled queries, baseline comparison, offline metrics, representative data, ranking regressions, online experiments, latency, and monitoring unintended business effects. Question 20. Why do you want to work at Elastic, and how would you contribute? Elastic appeals to me because it combines deep distributed systems engineering with products developers use to search, observe, and secure complex environments. I enjoy solving performance and reliability problems where design choices affect both infrastructure and user experience. I would contribute strong fundamentals in APIs, concurrency, testing, and operational debugging, while learning the product and codebase deeply. I also value open collaboration, so I would communicate clearly, seek feedback early, and connect implementation decisions to customer outcomes. Connect motivation to search, observability, security, distributed systems, open source, customer impact, collaborative engineering, and specific strengths you can demonstrate. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.